Okay, so welcome back to another video. In today's video, we have the following infinite product series of 25 divided by 777 to the power -1 to the power n, then multiplied by the fourth n of tangent x plus 1, then divided by 2n of tangent x. So here we have the association of a base, and then with the exponents, you can tell that this is actually an alternating series like so, and then we have some trigonometric functions in this expression as well. The whole process of tackling this problem is we're mainly paying attention to our exponent because really the base is not really exactly the important part. Well, it is in a sense, but we're not really going to pay attention too much of it. It's mainly because of the exponent. Simply, we're just going to rewrite the exponent in ways where if you can actually expand this down in a way, we can actually rewrite this in terms of a summation series, and we're going to use that to our advantage, but also use a couple trig identities to help rewrite specifically the trig function that we're also given and work our way from there. So other than that, let's actually just jump right in. So I just mentioned that the base is not important, but specifically what I'll say is that I'm going to define a variable k is equal to 25 divided by 777. So of course we're going to put this back for later in the end. So for right now, this is going to be our variable k. So this means the whole infinite product we're actually going to evaluate is defined as follows. So we have k, then to the power -1 to the power n, then we multiply this with tangent to the 4n of x plus 1, then divide by tangent of 2n of x, like so. So now let's actually rewrite our trigonometric expression in a way where it simplifies some stuff out. So doing so, we have the same product symbol, of course, -1, k, then to the power -1. All right, and then we see that we can split this into two fractions using the linearity from the numerator. So we have tangent of 4n of x divided by tangent 2n of x. They share the same base exponents. You just cancel that out. So other than that, we actually simplifies that down to tangent of 2n of x. And then we have plus 1 divided by tangent 2n of x, but we can actually use the trig law and say that that's actually equivalent to cotangent of 2n of x. So with this, now we can actually, since we have the base and then the exponent, we can actually use our rules of exponent and actually split this up into a product of bases with different exponent values. So really, it's basically just multiplying two infinite product series. So we have, the first product over here, n is equal to 1. So the first one we have would be is that this is just k, then times -1 to the power n, multiply with tangent of 2n of x. Then we multiply this with our product, just do the same thing again, but this time this is in association with cotangent -1n, then cotangent of 2n of x. So now let's actually expand these two infinite sums out and see what we can do from here. So first one we have, this is -1, then n. Well, actually I said expand, so that's what we're going to do, expand with the indexes. So we expand this out, so we have this is negative tangent square of x, then add this. This is the alternating sum, so we have a minus plus minus plus, tangent of fourth of x, then subtract tangent of 6 of x, keep going. And now next, this is dot just represents multiplication, so we expand this over here. So we have negative cotangent of square x, add this with cotangent of cotangent fourth of x, then subtract cotangent 6 of x, then subtract. Okay, we just keep going from there. Now, if we see how the representation follows, we can see that this is actually an infinite sum. So we can rewrite both of these exponents in the form of an infinite sum. So now we have the infinite sum, n is equal to 1 of, so this is alternating, so this is -1 to the power n, then multiply with tangent of 2n of x. Then the next one, this is the same thing, so k, and then to the power of the infinite sum, n is equal 1 of the alternating sum, so negative 1 to the power n, and then cotangent of 2n of x, like so. All right, so now we actually have to calculate these two products. Well, really, we need to, specifically, we need to calculate these two infinite sums associated with the exponent, so that's what we're going to do. We're going to start one by one, so we're going to first focus on this exponent, and then we'll focus on this exponent. All right, so let's now focus on our infinite sum of negative 1 to the power n, and then multiply with the tangent of 2n of x. So negative 1 n tangent 2n of x. So we rewrite this sum as a so everything is in powers of n, so I could just write that as one expression under that power. So this is just negative tangent of tangent square of x, and then to the power n, right? Now what we can do from here is that you can actually see that this is actually in the form of a geometric series. So since the index starts at n is equal to 1, so that means we have to use that formula for r is our radius of convergence, or excuse me, that's not the common ratio. And of course, that latter follows that it has to be strictly, it's the absolute value of that common ratio strictly less than 1, which is valid. Then we can write this with the formula. So this is negative tangent square of x, then 1 subtract, then minus the tangent square of x, so this becomes a plus. Then from here, you can actually just rewrite the denominator using the trig form. That's actually just secant square of x, secant square of x. All right, so we keep going further, then we can actually rewrite this as, sine of, or rather negative sine square of x divided by cosine square of x, then times secant square of 1 over secant square of x, which is just also cosine square of x, which indeed these cosine squares just cancel, so we're just left with negative sine square of x. All right, so now, so that's one exponent down. So let's see, so over here, and then now, okay, now moving on to the second exponent, which is instead, this is now the cotangent. So let's see, I think over here should be a good space. So now n is equal to 1 of negative 1 n cotangent of 2n of x. All right. Okay, so it actually just follows the same pattern from what we just solved. So let's see, n is equal to 1, so we can just write this as negative cotangent square of n. Then just use the geometric series, so you could write this as negative cotangent square of x. Then we divide this by 1, then minus, then subtract the top, but that's actually just plus cotangent square of x. In other words, the denominator is the same thing as cosecant square of x. And then we can just rewrite the form. So we have this as just negative cosine square of x divided by sine square of x. Multiply, so I just flip the reciprocal, 1 over secant square of x is just the same thing as sine square of x. Two of these cancel each other out, so we're just left with negative cosine square of x. Like so. Okay, so now that's the second one follow. So now I'm just gonna follow through from over here. So that says now that we solved our two exponents, so now this actually follows that this is just k to the power negative sine square of x multiplied by k to the power negative cosine square of x. Okay, so we can just use our rules of exponents. So share the same base, so we can just add the two exponents together, factor out the negative. So this is just k, write that a little bigger, k to the negative, and then sine square of x plus cosine square of x. Obviously, you know that this identity over here is the fundamental theorem of trigonometry. That's actually just equal to 1. So we have that this is just k to the negative 1, or in other words, this is its reciprocal 1 divided by k. All right. So we have shown that the following generalization over here, the product series of k to the power negative 1 to the power n of tangent 4nx plus 1 divided by tangent 2nx is equal to 1 over k. And so the last thing now is to plug k is equal to 25 over 777 under here, and we see that the final answer is, well, let's first just write it like this. 1 divided by 25 divided by 777 is indeed, just flip the reciprocal, is 777 divided by 25, like so. And there we have it. Final answer in the purple box, like so. Nothing too complicated. We just found the generalization for the base k, plug in our numbers, boom, there we have it. So yeah, that's pretty cool if you ask me.